Hi, everybody. This is a joint work with folks from UT Austin, Emmett Witchel's group, and my student at the Technion. So let me kick off this talk with a brief executive summary. So we built a native socket API and reliable streaming abstraction for GPUs. And our goal has been to build a better way of building GPU-accelerated networking servers and clustered applications. And so when we used this library to implement some of such applications, we figured that our framework allows to achieve substantially better results than the original GPU frameworks, and even beat the CPU by 50% in throughput, 60% in latency, and all that in only half of lines of code. So with that in mind, let me delve into the details of the presentation. So if you think about GPUs, they have been around for quite a while, and people have used them to implement parallel application acceleration pretty widely. So it is just natural to use them for acceleration of networking applications like data processing servers or MapReduce frameworks. And as a matter of fact, this idea has been around for a while. There have been several notable projects that showed impressive speedups for a wide range of workloads, for example, SSL offloading to GPUs, or MapReduce on GPUs, or even training deep neural networks on a cluster of GPUs, and accelerating web servers. So while these works showed really impressive results, they also showed quite vividly that building those applications required really heroic efforts. And if we look through the set of challenges that those folks went through, it is clear that we can categorize them into three distinct categories. One is pipelining and buffer management. Another is NIC GPU integration, and finally request batching. So these problems are kind of very well understood in this community, and they are really inherent to any GPU-accelerated server designs. So you might think now that I will go into detail about every single aspect of this, but I'm not. I'm not going to do that because understanding those issues in the context of GPU applications is not really essential for the content of this work. We're not going to solve these problems directly. We're going to sidestep them entirely by solving the problem that we believe is the root cause of all programming complexity of GPU-accelerated systems. And that problem is that now we're having systems that are entirely CPU-centric. All the data flow in the system is managed by the CPU entirely, and all the peripherals are entirely managed by the CPU. So this CPU-centric programming model poses some very difficult challenges that I will illustrate briefly. So let's think how we would design CPU server. This kind of really simplistic illustration of CPU server, the simplest you can get. You get the data from the network, you perform some computation, and send the results back. So that's easy. Now, let's say we want to accelerate this on GPUs. So you have this compute part. Let's write an efficient GPU algorithm and write it on GPU and run it on GPU. Okay, so let's add the GPU to the system, and what you would expect is that you would now have this kind of code in your system. Receive GPU compute, where you have super efficient GPU parallel algorithm, and then send. But that, unfortunately, can't be further from the reality. What we see here is the real flow of data in GPU-accelerated system, where first we need to batch the requests, put them into GPU memory, and as you can see, the code on the right is growing. Then you have to perform the computations on GPU on that batch, get the results back, and finally dispatch the results to the client. Now, if you think this is all, you're wrong. Because now you have to aggressively pipeline all this in order to get maximum throughput out of the system with all these data movements. Now, the question that you should be asking yourself now is, why did we write this code in the first place? What is this code doing at all? So this code, effectively, is a pure overhead. We are writing it in order to manage data transfers between CPU and GPU, in order to manage the GPU computations, and all this code is going to be run on CPU. We're going to implement this very code in small variations for almost every single GPU-accelerated networking application. Why are we doing that? It's because we have this CPU-centric design, and this is only one single design point that is not necessarily the optimal one. Let's take a step back and think about what we really have in our system. And think about GPUs not as co-processors, but as peer processors. And then it becomes suddenly clear that we need to raise the level of abstraction that we are dealing with, and we really need to provide the real I/O abstractions directly to GPU programs. We did that for file I/O. Now we're showing how to do that for networking. So this is the view of API or of the system that the GPU developer would see when one would want to develop servers on GPUs or networking applications on GPUs. So this is essentially an application code that you should write. And as you can see in the middle of this picture, you can write GPU native server, and we call it native because unlike previous GPU designs, there is exactly 0 lines of CPU code. So this is a GPU native server where you can use standard socket API, use reliable string abstraction, and know that now you can connect to this server from standard CPU client or from native GPU client. This interoperability is extremely important for us because we really don't want the clients to understand and to know, to be aware of the hardware that the servers are running on. So if this is the application view, what is going on inside the system? So this is the code that you're going to write. You're going to write it not on a CPU, you're going to write it on a GPU. And as you can see, CPU is not involved in here. There is exactly 0 lines of CPU code, as I said. So let's just drop it from the picture. We don't need it. Now, another interesting side effect that we get from this is that we can expose much finer granularity of GPU parallelism directly to the clients. So we don't need to perform request batching. We can do different requests, different stages. We can just inject the data directly into GPU memory and have GPU pick it up without having to invoke it for every request. So it hides a lot of the overhead. It eliminates it almost entirely. That is why now you can build really low latency servers on GPU. Last but not least, you get request pipelining for free, and you get automatic buffer management performed by the infrastructure. So hopefully I convinced you that having GPUnet in your system is a good idea. Now the question is how we build it. So essentially when we started this project, we had 2 main goals in our mind. One in our collective mind. So the first goal has been simplicity. And this can be achieved by providing reliable streaming abstractions directly to GPUs. And another goal has been performance, where the goal here is to perform data path optimizations under the hood. All right, turns out that in order to achieve these goals, you really have to work hard because with the simplicity goal, you really have to perform transport layer processing somewhere. It could be CPU or GPU, or it could be something else, and the question is where to put it after all. So let's start with the first design option. Let's do transport layer processing on CPU, and that would basically entail using the CPU network stack. So the data would flow into CPU memory, and then it would flow into GPU. Now, it is a very different design from the baseline design that we had, because now the GPU still manages the data flow. It still initiates the receive and send operations, but it delegates the actual processing to the CPU stack. The downside of this design, although it has been used in almost all projects that use GPU acceleration for networking, the downside here is that there is this extra CPU-GPU memory transfer, which really makes the performance much worse. So another option, kind of another extreme, is to put network data directly into GPU memory and then perform transport layer processing in GPU. Now, GPU programs really have fun with that because we eliminate the extra CPU-GPU memory copy. Also, we take advantage of this advanced hardware functionality that is called peer-to-peer DMA. This functionality allows peripheral device to communicate directly without involving CPU at all over PCI bus. The downside, of course, is that we have to port some of the transport layer processing on GPU. This sounds like a lot of fun. And another significant downside of this is that CPU applications would now have to access network through GPU. That sounds completely ridiculous, as a matter of fact. So if we don't want to use GPU for transport layer processing, we don't want to use CPU for transport layer processing, who's going to do this transport layer processing at all? So we are off to use NIC for that. And we're actually using the reliable RDMA messaging. So reliable RDMA messaging essentially allows one application to send data directly into application level buffer to another application over the network. And what is interesting about it is that by using peer-to-peer DMA functionality, you can put the data directly into GPU memory, into the application buffer there, or directly into CPU memory. So this is great because it basically eliminates the need for transport layer processing. It allows the data to flow directly into application at the application level. However, it's still insufficient for GPUnet because we want to provide reliable streaming. So this allows us to basically build streaming on top of RDMA messaging. So this brings the following 4-layer GPUnet architecture. The bottom layer exposes reliable channel abstraction to the upper layer. And this layer basically implements this reliable channel on top of the hardware reliable channel if it is provided. So this is the RDMA transport. Or it can use CPU to provide exactly the same interface, but basically offload all the transport layer processing on CPU. For example, for Unix domain sockets, this is absolutely necessary. Note that this is exactly the same interface that is exposed to the upper layers, so they implement reliable in-order streaming and eventually provide the streaming support to GPUs through socket API. Now, apparently, these first 3 layers implemented on GPUs are very important for simplicity because this is exactly where reliable streaming comes in and the socket API. Now, the performance is entirely dependent on the hardware support, and we still manage to get pretty good performance even without it. So we addressed a bunch of other issues. There have been some pretty challenging technical problems here, and I invite you to read the paper for getting this. Now, in terms of implementation, we have 2 versions of the library. One is for streaming over InfiniBand RDMA. Another is for Unix domain socket support for CPU-GPU communication within the same machine. It is important to note that our GPUnet streaming over RDMA is fully compatible with the streaming library over RDMA, which is called RSocket. So RSocket essentially is a drop-in replacement for socket. It's fully compatible for socket API. With socket API, and what is important that it allows us to build applications that are basically require no modification for CPU to communicate with GPUs. From the implementation perspective, we have 2 sides of this. On the right side, this is GPU side where all the API are implemented, the flow control and network buffers are stored. And on the left-hand side, there is GPUnet proxy that basically mediates the GPU access to the NIC. And we use it, for example, to provide shared port address space, right, with CPU. Now, as a fallback, we can use bounce buffers and CPU memory to get data into CPU first and shift it to the GPU in case there is no RDMA support. And this is done completely transparently for the application. In our evaluation, we extensively tested our library on a variety of applications, and we actually put a lot of effort in analyzing the different options of GPU native server designs. I will not cover that here. It's in the paper. Here I will talk about 2 important big applications that we implemented. One is in-GPU memory MapReduce, and another is face verification server. So let's start with in-GPU memory MapReduce. This is essentially a fully functional prototype of MapReduce library. It allows you to write your MapReduce kernels entirely on GPU. And this is essentially the first implementation of fully native GPU library. There's 0 lines of CPU code. Again, I emphasize that. And so we use GPUFS to get data from the disk and GPUnet to communicate between different GPUs. It is important to know that it is in GPU memory library because the shuffle stage does not spill out the data to the CPU. It basically sends the data directly to the receiver model in another GPU. So we were primarily concerned with the scalability of our system, and we implemented two kind of classic workloads, k-means and word count. So we ran them on a single GPU without any network support, apparently, and on 4 GPUs using GPUnet. So all those GPUs are located in different machines, and they use GPUnet to communicate over InfiniBand. The scalability numbers here are pretty good, as we think. The 3.5x for k-means and a little bit lower for word count. And the reason is that the word count is very IO intensive and much less CPU intensive. So there are not that many opportunities to hide inter-GPU communication overhead. What is really important to note here is that GPUnet enables scale out for GPU accelerated systems in a pretty straightforward way. We just put one GPU version, added, send, receive, and got it running. So this is another workload that we evaluated IO system with. Essentially, the idea is to build a security system that performs face verification in order to provide access control to a certain facility. And the idea is that there are many clients connect to a central server, send the photos taken, the photos gets analyzed, matched with the database, and the result returned. Pretty kind of easy to understand workload. Here the system is built out of, we have 4 machines used in the system. 2 of them are unmodified CPU clients that connect to GPUs through our socket library. And another is memcached, which is also unmodified and use our socket library to perform, to get requests over InfiniBand. The GPU server, we implemented we implemented 3 versions. One is essentially one that is not using GPU, another not using GPUnet, another is CPU parallel version with with multi-thread implementation. And the algorithm here is pretty straightforward. The data is received, then the features are extracted, the database is queried, and the match is basically performed. So again, the algorithm is quite trivial, I would say, at least at high level. So let's take a look at the actual performance results. So this is the latency throughput graph. On the x-axis, you can see thousands of requests per second in throughput. On the y-axis, it's latency in microseconds. So apparently, on the right-hand side and the bottom, you do want to be there because these are the best results with the highest throughput and lowest latency. On the left-hand side is the opposite. And this graph is essentially the graph where you can see the latency distribution. So you can see 99th percentile median and the medial 50% of requests. So let's take a closer look at the results. What you can see is that GPUnet beats all other implementations by a pretty significant factor in throughput and latency. And I emphasize only in half lines of code if compared to CPU version, but much higher factor over the GPU version that does not use GPUnet. So what is also important to note here that we are comparing single socket CPU and a single GPU here. Now, let's assume that you didn't have GPUnet and you wanted to use GPU, and what you can see here is that although GPU does provide a little bit improvement in latency, it is pretty bad in terms of throughput. What is also important here is that you get pretty large variability in latency in this version. And when we analyzed it further, it turned out that the latency variability comes because we invoke GPU for every request. And because that happens, it turns out that CUDA runtime somehow introduced some hard to understand latencies there, so that sometimes requests get handled very quickly, sometimes very slowly. Now, this is the last experiment that we did and that I will show here, which is a scale-up experiment where we're trying to use all the resources that we have on the machine. These are 10 CPU cores and 2 GPUs using GPUnet. We built 2 versions of the application. One is latency optimized, another is throughput optimized. And what is important to note here is that even the throughput optimized version is more or less has more or less the same latency as the version running on CPU cores, but it achieves 4.5x throughput improvement, which is equivalent more or less to 27 CPU cores running on this machine. So to conclude, we built a native GPU library for with socket API and reliable streaming. And I think we illustrated that CPUs and GPUs are now pure processors, and this kind of system design really allows to simplify the programming model and achieve high performance. Thank you very much.
Hi, Rodrigo Fonseca from Brown. This is really cool work. I had just one question. I understand that you implement a socket API for simplicity, but I was curious if you lose any performance by doing that, and do you have an idea of how much? If you had a more direct mapping, not bypassing the socket API.
I'm not sure I got the question, if you can repeat it.
So you're providing the socket API for the GPUnet programs, but you could bypass the whole socket API and provide something that's closer to RDMA. And then it would not be as simple, but you might get an extra boost in performance. I was curious if you have an idea on that.
Yeah, absolutely. This is a great question. Well, apparently there is this usability performance trade-off that we are trying to find the right balance. And yes, there is a pretty significant reduction in performance, primarily because there are extra memory copies inside GPU memory. And so we're now working on zero-copy API, which basically eliminates this overhead. And we are still trying to be compatible with sockets, but that becomes a little bit trickier.
Hello, I'm Pramod from MPS Uptodus. Pretty neat abstraction for providing sockets and GPUs. I was wondering, could you compare this with the GPU Direct technology, which allows you to do something similar? And especially the GPU Direct with RDMA, did you do some performance comparison with that as well?
Yeah, that's a great question. So the question has been, how does Socket API compare with GPU Direct RDMA, which is now technology to perform direct GPU communication? Now, let me put it this way. This is our building block. It's not that we are not using it. We couldn't build our library without GPU Direct RDMA in the first place. So we are building our abstraction on top of GPU Direct RDMA. And that's why comparing with that is kind of weird.
So when you talk about GPUs and CPUs, right? CPUs and servers in general, you're talking about event-driven and very asynchronous programming model, and where GPUs are really focused on a very data synchronous and very synchronous SIMD type of programming, right? And it seems like a very impedance mismatch to have one type of workload being targeted at another. And why? Just what? Do you have any thoughts on how you can actually achieve a speed up in a general case about offloading this kind of stuff?
Well, that's an interesting question. It's more philosophical, I would say. And I'm not sure that it's the right time and place to talk about it now, but I would be happy to follow up. I would just say that what GPUnet gives you is the freedom to choose where to do network API. And if your workload is sufficiently parallel and pretty well suited for GPU, why pushing the boundary of CPU processing and moving it back and forth?
Okay, I'd love to talk to you offline. Rajesh from Facebook. Thank you.
Thanks.